I can do this for hours, but first, let me tell you how I made it. What do we have here? We have a robot arm with multiple parts of potentially different but fixed lengths. And we have a ball at position xjyj that we can move by clicking somewhere. Let's name it, for example, Frank Abagnale Jr., because our goal is to make the robot arm catch it. In other words, making the end effector position close enough to the ball position. We can think of it as a minimization problem, where the goal is to find the right values to minimize the Euclidean distance between end effector position and ball position. But a path length is fixed. We cannot control it to make the arm reach the ball. Instead, what we can control to reach our goal is the joint angles, the angles between each successive pair of parts that we name theta. With k parts we have theta 1, theta 2 until theta k. Note that here theta represents the angle relative to the ground, the global x-axis, not relative to the previous part. In a minimization problem, we have variables to choose a value for, theta in our case, in order to minimize an objective function, the Euclidean distance between the end effector and the ball in our case. But wait, ball position is given as input. What about end effector position? We need to be able to calculate it starting from theta and lengths of arms. This is where forward kinematics comes in. Let's take the simple case where the arm has only one part. It would be the worst baseball player ever, by the way. We have the length L1 and the angle theta 1, and assuming the arm starts from 0, 0, we want to find x1, y1. Basic trigonometry knowledge, x1 would simply be L1 times cosine of theta 1, and y1 would be L1 times sine of theta 1. Now, what if it had two parts? We have the length L2 and the angle theta 2. In this case, we calculate x1, y1 as we did, then to get x2, we simply add to x1 L2 times cosine of theta 2, and to get y2, we add to y1 L2 times sine of theta 2. Three parts? No problem, same logic. x3 is x2 plus L3 times cosine of theta 3, and y3 is y2 plus L3 times sine of theta 3. With this three parts arm, the end effector position, which is x3, y3, because it's the endpoint of the last part, is simply L1 times cosine of theta 1 plus L2 times cosine of theta 2 plus L3 times cosine of theta 3 for x, and replace cosine by sine to get y. We can easily generalize it for an arm with any number of parts. We get x equal to the sum of Li times cosine of theta I and y equal to the sum of Li times sine of theta I. Alright, we now know how to evaluate an arm configuration. Because we know how to find the end effector position starting from given angles, then we just calculate the distance to the ball. But the question is, how to find such a configuration? That process is called inverse kinematics. Well, let's take the simple case where we have only two parts, so we need to find theta 1 and theta 2, which are of course continuous and bounded by 0 and 2 pi. From here, we can draw a 2D plot, with theta 1 and theta 2 as dimensions, and the value representing the objective function value. In other words, by choosing that specific combination of theta 1 and theta 2, how close to the ball we would be. And this plot represents a continuous solution space, with the global minima representing the closest we can get to the ball, and it's the value we're looking for. That's for two joint angles only. With k joint angles, we would obviously get a k-dimensional space, because the solution would be in k dimensions. And to find an optimal or almost optimal solution, we have a bunch of techniques that we can use in our context. We can use classic IK algorithms such as CCD, Fabric, but today I want to use a technique that we don't often hear about, PSO, Particle Swarm Optimization. We need to have a full video on the topic, but in brief, PSO is a meta-heuristic, nature-inspired technique that works this way. Imagine a swarm of fish looking for a spot with a perfect temperature, and they can measure temperature of their current spot so they can evaluate how good it is. Looking for the perfect spot requires exploring the ocean. How would they do that? Assuming that they start in random positions, we now need to give them a velocity, the direction and speed they follow. In PSO, velocity is influenced by three elements: its current value, because we may not want it to change drastically, its own best position so far, but also the best position so far of the whole swarm, aka the global best position. To balance the influence of each one of them, we have three hyperparameters: the inertia weight W, which is the factor by which we multiply the current velocity, the cognitive coefficient C1, which is the factor by which we multiply the effect of the personal best position, and the social coefficient C2, which is the factor by which we multiply the effect of the global best position. We also have R1 and R2, which are random numbers between 0 and 1 that are sampled from a uniform distribution again at each iteration, helps including some stochastic behavior. And we get this formula for calculating the new velocity that we add to the current position to get the new position of the particle. And this is what happens for a single particle during an iteration. But in PSO, we have a swarm of particles, for example 10, and this operation happens simultaneously for all of the particles at once at each iteration. And of course, at the end of each iteration, we check what particles found a better position than their current best position, and check if one of them is better than the global best position. Note that evaluating positions is done using a fitness function that calculates how good is the solution represented by that solution. We repeat the process for a given number of iterations, and we get this beautiful swarm of particles all searching for the optimal solution. At the end, we just grab the global best position found, representing our solution. Nice. Now how to apply PSO to our case? Remember that our goal is to find what angles will get our end effector to the ball. So a solution is an array of k values between 0 and 2 pi, where k is the number of parts. And a particle in PSO represents a single solution, so we create many of them, depending on the value of non-particle's hyperparameter. We give to each one of them a random position, aka a random value for each angle, and we let the process run for num iterations. At the end, we grab the global best position, assign values of its angles to angles of our robot arm, and we should be really close to the ball. Amazing! Humans programming a simulated swarm of fish to control a simulated robot arm. Cool, but for now, we made the calculation part only. What about the visual side that will make your non-technical friends go wow? Let's dive into it. For that, let's use Matplotlib. We need a figure, a ground horizontal line, a line plot for each part with a dot at the extremity of the line to represent the joint, and a circle to represent the ball. And we want that each time we click inside the axis, the ball moves to that position. Theta is calculated again by running PSO from scratch, and line positions are updated to show the new position of the arm. It's working, but the robot arm is instantly teleported to its new position with no intermediate path, which makes the animation less interesting. A way I thought to fix this was to calculate the final solution of PSO in advance, but not move the arm to it directly. The idea is to interpolate positions between old theta and new theta, and make progress in the percentage of the animation at each frame. We start at 0% of the animation, then at each frame we increase the percentage until reaching 100%. And intermediate theta is simply old theta plus p times new theta minus old theta. Note that we can increase percentage by a fixed amount at each frame, for example 10%, but in my opinion, it would be better to make the arm go fast at the beginning, then keep slowing the progress the closer it gets to 100%. We can do so by increasing p by 1 minus p divided by a, with the constant a being greater than or equal to 1, and the closer to 1 we set it, the faster p will go to 100%. And by setting a to 5, this is our result. The animation is working smoothly, but sometimes when translating from an angle to another, the arm is rotating across the longer direction, which is less efficient. Say we want to translate from 20 degrees to 300 degrees. Our animation is sometimes going 20, 30, 40 and so on until 300s, while 20 degrees is closer to 300 degrees if we go backwards, 20, 10, 0, 350 and so on. The issue is in our delta formula, the one that tells us the difference between new and old angle. The right formula, the one that goes from the shorter direction, is this one. Nu theta minus old theta plus pi modulo 2 pi minus pi. By replacing it in our code, we get interpolations that go from the shorter direction. And finally, we got our smooth animation of a robot arm catching a ball that we can move by clicking somewhere. However, we can have some improvements. First of all, if we keep clicking on the same spot or almost, PSO runs again, but it sometimes finds a totally different theta configuration, even if it leads to the ball. That's due to the randomness of the algorithm found in initial particle positions and R1 and R2. That's not very efficient in terms of energy needed by the robot arm to make the moves. We don't want small changes to the ball position to produce totally different arm configuration. And this is why instead of penalizing a position if it's far from the ball, we can also include a penalty if the angles are far from angles of the solution with the precedent ball position, the precedent PSO run. That's one thing. Another thing to improve is avoiding parts collision. We can notice that some arm configurations, even if they lead to the ball, have their parts scrambled, which may not even be possible physically. This is because we are solving inverse kinematics without constraints, but constraints can be included in inverse kinematics, such as avoiding collisions between parts. It would give us a more realistic robot arm. But we will stop here for this video, where we discussed forward kinematics, inverse kinematics, particle swarm optimization, matplotlib animations, and more is to come in the next videos, because after more than 2 years of not posting, Inside Code is finally back. You can notice that some things changed: visual elements, types of animations, and even content type. The channel was focusing on explaining algorithms and data structures in an academic way, which didn't excite me anymore at the end. But right now, we will also discuss other related topics, such as data science, AI, operations research, and more. We will also include way more real-life projects, experimentations, tutorials, and a lot of other video concepts. You can even suggest in comments what type of content do you want to see covered here. We can also mention the animations. By the past, I was making animations exclusively using PowerPoint. Yes, what a mistake. But it gave good results, as you could see in previous videos. However, I feel like I reached its limits, because yes, it's quite limited. And definitely not the best for technical animations, especially for animations that require specific calculated values, such as in this video with the angles and stuff. This is why I'm switching to Manim and Matplotlib plus some post-processing elements added in the editing software, which gives way more freedom and possibilities in terms of animations, which can even be reusable. In brief, those are a lot of changes for Inside Code, and more ideas will be experimented in the future. I hope you will like this transition. You can find code for this video in the description. Give me your feedback in comments, and see you in the next one.